Chalk. Merda. Ok. Ok. So, ok. So I ring the bell once again. Okay. Thank you very much. Okay. So thank you for surviving till this point. I trust me, today's lecture is going to be worth it. So, okay, recap. So we have seen, no, this general ideas, no? We have played a bit with the heuristic, and we have seen 2D CFTs, no? And in that context, so apart from the basics, we have discussed the enrichment by symmetries. And then we have discussed the Ising example in details. And also a constraint on RG. Okay, so in part 3, we have started looking at topological operators in higher dimensions. And we have seen this notion of higher p-form symmetry. We have seen examples in Maxwell theory. We've discussed screening and the emergence of discrete versions. And we have discussed the example of Yang-Mills theory, the interplay of spontaneous symmetry breaking and dynamics. For instance, the relation between one-form symmetry and confinement. Okay. And then we had started moving towards more general examples, no? So we have discussed these ideas of higher associators. And as a first example, we gave the notion of higher group. No? And so all of this, all of what we have discussed so far, was in the context of symmetries that are still very, very much group-like, meaning that their fusion rule is still one-dimensional. No, they are so far. Symmetries were still group-like. No, the product of this generalized symmetry defect that we defined, no, is still the group law. No, it still satisfies the relations of a group. There is the fusion channel is one-dimensional. No, and that one is the case also for the higher groups. But before continuing, so now the next step, no, in the program of the course is to graduate to cases where the fusion rules, the fusion channels are more interesting, where you don't have one-dimensional fusion rules. You have more fusion channels. You get something that generalizes groups. Okay. So next step is to find more general fusion rules which give rise to symmetries beyond groups in higher dimensions. No? In the case of 2D, we have seen that we get something that goes beyond a group. Each time in the fusion, we get a relationship where we multiply two things and we get a sum. No, that's not a group multiplication. Group multiplication always look like this. No? And so far, the defects that we have constructed always multiply like groups, maybe like higher groups, but still they are very much group-like. Before we dive into this realm, I want to revisit a little bit the discussion that we had yesterday about these 2 points, because I was trying to cut some corners, and I think I cutted too many. And because I was hoping to arrive to chapter 4 in the course, which is about this topological symmetry theory, but I think it's probably better to omit chapter 4 and to spend some more time on chapter 3. Okay, and I will give you some references for chapter 4. So in particular, references for what we have discussed about higher groups. Among the things that I cut out last time, there were the references. There is a very nice paper by Cordova, Dumitrescu, and Intriligator. And then this other work by Benini, Cordova, and Sin. And then the reference for this higher gauging operation is a work by Rumpedakis, Saif Najri, and Shao of 2022. Okay. So I want to discuss now a little bit more about this relation between anomalies and associators. No? No? So we have seen that in the general discussions, no, you have seen that whenever we have a fusion rule, there is a relation that arises. No? We have our 2 defects. No? We fuse them and we map them into their fusion. No. So here, like maybe the right way of writing it, this would be what I mean here is like an element, say decay, that belongs to the fusion of these 2 when we decompose it into simple objects, no? Something like this. No? This is probably the right, a better way of denoting it. So I would like to denote these elements for keeping track of these indexes. I will denote an element like this with D12. So D12, you have to think about it as if it is an element in the right hand side of this expression. So just pinpointing one of the elements out of this sum. No? And then we have seen so this picture is very very two-dimensional. These are lines, but in general, in our symmetry category, we expect these defects to be higher dimensional, no? And so these fusions will happen along interfaces, no? Look like this, where so this guy will be D12, no? So here you have D1 and D2 in the tensor product, and this interface is establishing a morphism between their tensor product and this element in the fusion. No? But what I wanted to stress is that like the things that in the context of two dimensions were topological points, no? Two dimensions, they were topological points. Now they are topological interfaces. They are higher dimensional. Okay. Now, in two dimensions, moreover, we have seen that if we consider the associativity of the product, no, this is related to a diagram where we exchange the order of this operation, no, and we say that there is a relation between this diagram. These relations are encoded in F symbols, no. But now you see the associativity. Let me redraw it a bit bigger. No? If you have more room to play with, like in the case of these topological defects, the associativity can be taken care of, no, by an interface of interfaces. Okay, so this is your first defect, no? This would be the second one. This will be the third one. It goes behind. Like this, no? Now, so this edge here is moving in this direction, no? This edge here is going in the other direction, no? Okay. And you see, take some time to look at this picture, no? Let me comment a little bit about it, no? So here we have the first defect, here we have the second defect, and this one is an interface like this that brings them together, giving rise to a defect of type D12. No? Above, we have the defect D2 and the defect D3, and here they are merging along a different interface that give rise to the defect D23. Okay. Now here we have a new interface that takes D1 and D23 into an element D123 that belongs to the tensor product of our three friends. No? And now here below we have another interface. This one is taking D3 and D12 into this defect. No? So here I should have used it, but unfortunately we are a bit monochromatic. I should have used it like 4 colors in a sense. These are 4 different morphisms, no? This one is taking 1 and 2, 3 into D1, 2, 3. This one is taking D1, 2 and D3 into D1, 2, 3, no? And you see that, they meet at a special point here, no? And try to color in pink, no? And you see, this point here is a topological, in this diagram, we are limited, our capacity of drawing are limited to three-dimensional drawings, no? So if you think about these as surfaces, their morphisms are given by lines, no? And the morphism between morphisms are given by topological points, no? So you see that the associativity, which before was something that gave us a relation between two fusion channels, which we expressed using the F symbol, in the context of higher dimensional topological defects, is something that we can take care of with an interface. No? So what before was a relation now becomes extra data in the symmetry category. No? So this is part of, well before I gave you the F symbols and they had to satisfy a consistency condition, no? Now this consistency condition is taken care of by this topological interface. So it's part of the data that construct the category, okay? Now, instead of making this complicated drawing, we can try to summarize them just writing arrows as if they are morphisms. Morphisms are maps, no? So each topological interface defines a map, no? So the one above is a map from D1 tensor D2 into D1, 2, no? The one here, what it is, so we have D1, D2, D3, no? This interface here is a map, no? That brings it into D1, 2 tensor D3, because D3 is always there, no? In the background. And then this one here is taking D1, 2 tensor D3 into D1, 2, 3, that element over there, no? The one above is taking this collection into something that looks like this, no? Where we have fused D2, 3 before, and then we are left with D1. And now we are taking it down to the same element here, no? So these ones, these arrows here, are the green interfaces in the diagram, no? The red dot, no, is a relation of this type, no? It is a morphism between morphisms, okay? So this is your first encounter with a higher morphism. No? And notice that higher morphism happen in higher codimensions, no? So if you start with defects of codimension of dimensionality k, no, then the morphism will be in dimension k minus 1. No? The higher morphism over there happens in dimension k minus 2. No? They are interfaces of interfaces. Okay? So now that we have understood how to draw these diagrams using arrows, we can consider, for instance, what happens if we bring together four people, four of these defects. No? No? Four of them, yes. Is the dot, yes. No? So you see, we can go and fuse these two first. We can fuse before the one that are in the middle. Or we can fuse the last two together before. And now, these ones we can map to the fusion. I can fuse these two together or these two together, and so I can get a map like this. No? And then, well, this one we can decide to map to fuse D12 with 3, no? And then we have a map also from here to there, because we can fuse D1 with D23 and go here, no? And this one we will map into D1234. So an element in the fusion of the 4 objects. And then we have a map also here, from here to here, because we can take 1, 2, and 3, 4 and map them here. Down there, we have a map from D1 into D234, fusing D2 with D34. And from here, we can go back there. From this element here, you see we go down here, because we can fuse D23 with D4 in a different channel and get here, no? So you see, this one was a line, this one is a square, and this one is a cube, okay? So each time, the hygermorphisms are encoded in diagrams that acquire one higher dimension. If I study the fusion of 5 objects, I will get a hypercube, okay? Well, I will get I will draw it, I will still be able to draw it on the board, but the topology is that of a higher cube, no? Every line corresponds to a morphism, every face of the cube corresponds to a higher morphism, no? The cube itself corresponds to a morphism, so this is a morphism, this is a two-morphism, because it is a morphism between morphisms. And this one, the cube itself, once I shrink it down, no, encodes something which is in codimension, say, k minus 3. It has dimension, sorry, it has dimension k minus 3, no? So this one is a so if this one is a two-morphism, no? This one would be a three-morphism. No? The cube itself. You see? Yes. So this one is a surface, okay? This one is a surface. There is a surface in the middle, no? And the surface in the middle has this boundary here, no? You see, like it goes like this. And the third surface comes here, no? And they meet at a point. Three surfaces they have to meet at a point, no? Okay. So you see, the story continues, no? The higher the morphism, the smaller the dimensionality of the corresponding topological interface, no? This one, if these are k-dimensional, this one is k minus 1, k minus 2, k minus 3, no? It becomes smaller and smaller, no? And you see, eventually, we will end up in a situation like the one that we had in 2 dimensions, where we had something that happens at a point, and the next associative diagram becomes a constraint on it, no? So the pentagon identity, no, that we got was a constraint because the F symbol, if you like, was associated to this diagram, was associated to this morphism, but the F symbol happened at a point in our construction, in 2 dimensions, no? And now the next associativity diagram, since the product has to be associative, becomes a constraint because we don't have any more room to make it happen because we have exhausted all the dimensions. No, we cannot fold our defects in such a way to accommodate the associativity of the product. No, and so once you go to the associativity that involves as many objects as you end up not being able to accommodate by just folding the defects, no, you end up with a constraint, which is the analog of the pentagon constraint for the F symbols. No? Okay? So if you think about it, the pentagon comes from this cube, because you see, there are in the cube there are 6 faces, it's true, but the top face doesn't say anything, because here we are fusing these two together, here we are fusing these two together, and here we are fusing these two together, and here we are fusing these two together, and this operation commute, no? So the top face of the cube doesn't say anything, and you are left with 5 faces. Those 5 faces are the 5 F symbols involved in the pentagon identity. Okay? So the top face doesn't impose anything. The 5 faces that you are left with, they are the pentagon identity. No? So this was a bit abstract, no? And it is related to this approach by Carqueville that I discussed yesterday. But now let's make it concrete. So let's look, yes. What? Oh, you can. If you like, you can. But what I'm saying here is that the message that I'm trying to convey is that associativity of the product can be taken care of by the fact that these surfaces are topological. So we can fold them on top of each other. No? So as long as you can fold them, you can create an interface that keeps track of the associativity. No? So while in 2 dimension the associativity became a constraint essentially immediately and gave us the pentagon identity, in higher dimension, when you consider these higher dimensional surfaces, there is more data that goes into it. No? All of these topological interfaces you have to compute, and it's extra data that you have to specify to fully characterize the symmetry category. Okay? And it is this data that keeps tracks of things like the fractionalization effects in higher symmetries, if you have heard about it. But it is data which is extremely interesting. And now what I want to do is to give you examples about the relation of these type of structures with the anomalies in lower dimensional field theories for ordinary symmetries. No? So consider, for example, the case of quantum mechanics. No? Quantum mechanics, you have a line, so there is only one dimension, no? And the insertion of symmetries already happens at points. Okay, so there is not so this one already the associativity is a constraint in the case of quantum mechanics. Okay, you don't have room to accommodate anything essentially. No? So quantum mechanics, you have unitary symmetries, say, or anti-unitary. Let's consider the unitary case, no? And they multiply according to the group multiplication, no? But their action on the Hilbert space, no, only can always be rescaled by a phase, no? So you can always rescale the symmetries by a phase, because what matters are just the rays in the Hilbert space. So you have always the freedom to rescale your symmetry operators by a phase, because it's a quantum mechanics, so you can do it. No? So if you think about it, no, if you think about this product, therefore, you can also rescale this one by a phase, no? That now depends on these 2 elements. Okay, this is part of the way you can define your action of the symmetry in quantum mechanics, because you're free to rescale it by a phase. So what is that associativity says? Associativity says that if we bring together two objects like this, no, this has to be equal to the product of these two with that one. No, so this is the associativity of the product. No, but what happens if we decorate it with these phases? No, you see that. So from this one, we would pick up a contribution which is like G and G prime, G double prime, no? And then from the first one, we get a phase that looks like alpha of G prime, G double prime, no? This would be the phase that you get from this side by this rescaling operation. On this side, what do we get? We get something which is related to G and G prime and G second plus alpha of these two, so G prime, G and G prime, no? Okay. So if you have a function, no, from your group into U1 that satisfies this condition, this is called a two-cocycle condition. No? And now from the freedom that we have to rescale our operators by phases, we see that we can ask ourselves, but can we get rid of this alpha by just doing a rescaling like this? And you see that if you do that, the only thing that the best that you can do, no, is to shift alpha by something that looks like this. You can shift it by a theta of GG prime minus theta G prime. No? So at best, by redefining the action of the operators, no, by this local counter term, if you like, no, you can take alpha and shift it by this, no? And this type of shift, this action like this is the statement that you are shifting alpha by a co-boundary. So you see, what you obtain here, you have this cocycle condition, you have the possibility of shifting it by this change, no? This one is a cohomological problem, no? So you can get rid of this phase, no? You can get rid of this phase, provided you can solve for a two-cocycle, which is trivialized by shifting by a coboundary. No? So the cohomological problem, alpha, is a class in what is called the second group cohomology with coefficient in U1. No? So this e to the I alpha, no, is this class. No? So this gadget here is what decides whether your representation is projective or not. No? Classifies projective representations. Okay. So yes. So this one here, this one is a cocycle condition. So this one is the statement that there is a differential, no? The differential in group cohomology, which acting group cohomology is just a cohomology that you define in terms of functions of n variables that take n copies of your group and map them into U1, no? And then you define you want to check which of those functions really depend on those n group elements up to consistent shifts, no? So the differential is a bit it's not a standard differential. It's a differential in group cohomology. But still, this is a cohomological problem. So this would be, for instance, the differential that a function of two elements that is obtained from a function of one element of this type, no, would be the differential of something, no. I don't know if this but so it's a well developed theory that I won't have time to discuss, but that from the physics perspective it's very very natural, no. So you see, you have a cohomological problem. You have to find a function of two elements of your group, no, that satisfy this condition up to this relation. Okay, so this one is a relation between these functions. Okay. Oh, this is a symbol. It's just it's called oh, I don't remember. uh, um, is the classifying space for bundles of G. But in this case, if you think about a group, a finite group, you can, I mean, it's just a notation, if you like. We could call it also like this, if you prefer. It's not a problem. Like, this is just there to remind you that we are using this group cohomology. Okay. So what I'm saying is that here we have a class, no, depends on two variables, so belong in H2. This action here, if you like, is the shift of a theta. So it's something that takes a function of one and defines a function of two, no? And this one is the statement that d of alpha is 0, if you like, no? So from this perspective is an element in this cohomology, yes? Well, an exact element is, you know, like you have to take the image and mod it out by the kernel, no? So this would be, this one is the condition for the kernel, and this one is the condition that you can shift it by the image of something, no? So these, in particular, classify projective representations. If you remember the lectures that you've seen this example of quantum mechanics, a particle on a circle, no, in quantum mechanics, and there you found that there was an anomaly related to the projectivity of the representation, no. So this is always like that. All anomalies arise from projective representations in quantum mechanics, no. If the representation on the Hilbert space is projective, it is anomalous, no. And as you see, they are captured just by the condition of a of an associator. In this case, it's just the first associativity, because inserting the asymmetry in quantum mechanics is already a condition at a point, no? The next condition is the one associated to the F symbol, no? Because I'm using that equation, no? Sorry, maybe it was too quick, but like, you see, this is the equation I start from, and now I shift UG into e to the I theta G times UG. So I get a contribution from theta G, a contribution from theta G prime here, no? And then here I have theta GG prime on this side, and I'm shifting alpha. I redefine, yeah, I have always the freedom, no? I have always the freedom to redefine all the symmetry operator by a phase, no? Because the representation is on the Hilbert space, so I can shift all of them by a phase that depend on the group element, and it doesn't change how it's on the states, no? And this freedom is what gives rise to this freedom of shifting it, no? So if I want to, the question is essentially, this is a central extension of the representation, no? And the question is, can I get rid of this or not? And to get rid of this, the only freedom that I have is to rescale the action of the operators, no? And this defines this shift. The associativity gives the constraint that these phases have to satisfy, no? So this is an example of what I was saying, no? We have our symmetries, associativity give rise an appropriate level of associativity. In the case of quantum mechanics, the first one, no, give rise to a constraint, no. The non-triviality of that constraint with respect to the freedom of rescaling our operator, our symmetry generators, captures the anomaly in the context of an ordinary symmetry. No? These are group symmetries. So there is no room for ambiguity. There is only one fusion channel in the group-like case. No? So let's consider now the case of two dimensions. No? In two dimensions, we've seen that the thing that happened at a point, no, is the associator of three. Is this diagram. So we go from here, which was the case of quantum mechanics, to here, no? And the constraint that we obtain, no? So no? The constraint that we obtain is the pentagon identity. No? And the question becomes, which of these pentagon identities is non-trivial up to the possibility of rescaling these defects and these topological points by appropriate local counterterms? No? And so this also becomes a cohomological problem. And it's just the next class in that context. So it parameterizes now. It's parameterized by an element in the third cohomology of your classifying space with coefficients in U1. So it's a class in the it's now a three group cohomology class. No? So if this one is non-trivial, now you have an anomaly. No? Okay, so the vanishing of the anomaly is the fact that that class is zero, is the zero class. When this one is the zero class, you see that you can deform these diagrams at no cost. No? So the idea is that, so if you have an ordinary symmetry, this would be a diagram, I don't know, like this. No? Here you have the associativity of 3. No? No? And so naturally this one is associated to and the difference between this one and that one is a class in 3 group elements. No? Here you have 2, here you have 3. Okay. And the constraint that you get on this class is the pentagon relation. No? And the cohomological problem that you obtain, therefore, since it depends on 3, is in H3. No? The non-triviality of that class signals the presence of an anomaly for an ordinary symmetry in 2 dimensions. No? Yes? That's gravitational anomaly. It's a different story. No? This is an anomaly for this image. It's an obstruction to gauge it. No? Remember, when I said, when can we gauge? You remember we discussed about the F symbol. No? We discussed about the possibility of relating this diagram with this diagram, no? Like this, by S-duality without picking a sign. No? The fact that we can do this is related to the fact that we can perform these deformations of the networks of topological defects without picking any extra phase. If we start picking up phases, then the structure of the network of topological defects will start depending on the triangulation we have chosen, no? And so it's no longer going to be gauge invariant. So having these non-trivial phases that emerge when we try to manipulate our networks becomes an obstruction to gauge it. Okay? And so, not surprisingly, no, if you go in higher dimensions with an ordinary symmetry, you see in D equal to 1, we get a class in H2. In D equal to 2, we get a class in H3. In D equal to 4, we'll get a class in H5. No? So in general, we get a class in HD plus 1, no, of this BG in U1. No? And this class is captured by a higher associator of the appropriate dimensionality. No? There is a cohomological problem that arises essentially in the same way, and give rise to this class. And this class is what parameterizes the anomaly for a general symmetry, a general finite symmetry in that dimensionality. No? If you have a higher p-form symmetry, no? What happens? This happens because ordinary symmetry defects have codimension 1. No? Ordinary symmetry defects have codimension 1. No? Now, if we start from a higher p-form symmetry defect, the dimensionality here will be smaller, no? Because the topological defects for higher symmetry are smaller than the ones for ordinary symmetry, no? So this will affect our cohomological problem, because if we start folding smaller things, we will hit the point earlier. You see what I mean? Is it clear? So here, for instance, we started folding surfaces, and after we started looking at the fusion of 3, we got the point. No? So if you take a one-form symmetry in 4 dimensions, no, you would be folding surfaces, because a one-form symmetry is codimension 2 in 4 dimensions, so the topological defects are surfaces. No? So you will get to the smallest possible intersection, the smallest possible topological point, earlier if the defects are smaller. Okay? And this has an effect in shifting the degree of this classifying space. So if you have a p-form symmetry, you get a class which is still fixed by the dimensionality of the space-time, no? But now in a higher space. No? So in general, this is the anomaly. And it is still computed in the same way. Okay? So you have to think about this index as an index that tells you what is the order of the forms that you use as backgrounds for your symmetry. No? So for zero form symmetries, it is 0, it is 1. And for higher p-form symmetries, it is p plus 1. No? So these are the anomalies. This is the relation, if you like, between, in the case of ordinary symmetry, there is a relation between these higher associativity diagrams that you can compute using your topological defects and the anomalies. They detect the anomalies. No? Now you have learned that anomalies are supposed to match along RG flows. No? So in the case of these symmetry categories, this will happen. The higher structure, all these morphism, all these intersections, if the RG flow preserves it, will be preserved by the RG flow. No? So in the case of ordinary symmetries, these are just captured by these phases. But in the more general case, there are more fusion channels and there is more structure. No? So yesterday we discussed the case of higher groups, which is a first instance of a symmetry which is more of a categorical kind, where you have some zero form symmetry that mixes with a one form symmetry. No? So we spoke about the case of a zero form symmetry that was mixing with a one form symmetry, and this was related to a current conservation equation of this type. And here we had a k, 2 pi, fa2, wedge star j2 of p. No? This one is the curvature for the background field of the A one-form symmetry. No? This coefficient k is an example of a new RG invariant. It's something that arises from a higher morphism in the category. It happens, you can detect it when you intersect 3 surfaces together. No? But while in the case of ordinary symmetry, at that point nothing happens. No? In the case of higher groups, at that point, a one-form symmetry defect emerges. Okay? So this invariant here is parameterized again by a group cohomology class, which will eat, say, 3 group elements here, no? So it's something that is parameterized by a three-group cohomology class that will eat three of the elements of the zero-form symmetry, and give rise to an element that now is in the one-form symmetry. No? So it takes three of them, and at that point spits out an element in the one-form symmetry. Okay? And I stress, these things, these coefficients, these Higher group coefficients, are RG invariants. So they have to match along RG flow, they have to match across dualities, no? Exactly in the same way as the anomaly coefficients do in general. No? So these have to these are but they are new. They are extra data. No? So the Higher group structure constants are examples of extra data that has to match across RG flows. No? This is the first instance, the first example of a symmetry where you don't have just isolated groups just shifted in the dimensionality of the defect. No? The P-form symmetry that we've seen yesterday, they are just a copy of U1, but it will act on lines or on surfaces. No? In this case, in the Higher group, no, you have a thing that acts on line, a thing that acts on point, and they mix. They mix when three of the defects that act on lines come together, you obtain out of that a defect that acts on points. Sorry, when three defects that act on point come together, you obtain out of that a defect that acts on lines. Okay, so this is the if you like, the distinction, no, between an ordinary group and a Higher group. That when you start fusing the defects in the Higher group, on top of just their fusion, you obtain also defects that will act on other extended operators. And yesterday, using just the ABJ anomalies, no, we showed that it is very easy to construct examples in 4 dimensions that have Higher group symmetry. It's simple. It's just a matter of finding the right charges for your Weil fermions you start from to satisfy, to find a solution of this equation. Okay? So the Higher groups are a thing. They are there in simple examples of QED-like theories. No? So now the plan. So this is essentially what I wanted to say yesterday, and I tried to compactify in 10 minutes, but I think I would have done. I did some harm to the subject. Like, it's nice, so I wanted you to be aware of it. No. And so now you see. So you see that there is this extra structure which starts emerging. No? And there is extra structure already in the case where the various levels of the morphisms of your category are groups. No? In the Higher group case, no? You have a one-form symmetry group and a zero-form symmetry group that mixes. In this case, this is called a two-group. No? But you can have n groups in general where you have a mixing between the zero form, the one form, the two form, no? Until the n-1 form symmetry, no? This would give rise to an n group, no? And in this case, you will have a lot of structure constants, no? Structure constant that says how from these you obtain one of these, how from these you obtain one of these, and so on and so forth, no? Yes. The codimension, yes, yes. No? Yes. Yes. So you have you always have a yes. And in particular, what I want to stress is that if you look at this equation, you can see that the one form symmetry is a proper subgroup of the Higher group, because this current is conserved as usual, but the zero form symmetry is not. The relation that you have to think about is something where, like, you have a map, say, of the one form symmetry into the Higher group, no? And then the zero form symmetry arises, but arises from a quotient, no? And quotients are not subgroups in general. Okay? And if you have a Higher group, you have a generalized version of this diagram that says which elements is a proper subgroup and which one is a quotient of what. Okay? This diagram is called a Postnikov tower for culture, but we won't have time to delve further in the Higher group structure, because we want to graduate beyond groups. No? So far, all the fusion channels of these defects were one-dimensional. Now we want to go beyond. Okay? They're one-dimensional, which means that they can be captured by appropriate group homology classes. In this case, this. In that case, that. But it's still like a phase. You don't have to think. These are not complicated things. It's just you start fusing this thing, and at a certain point, a phase pops out. Okay, so it's still like very one. The fusion is still very simple, still very one-dimensional. You try to bend these defects, you fold them, and a phase comes out. A phase times another topological surface comes out, but they are still one-dimensional types of fusion channels. Okay, now we are after something more general, something where we start fusing the defects, no, and we get something more than just a phase, no. In that context, the relation with anomalies is complicates incredibly. The theory is this theory developed by Carqueville on orbifoldings, no? But I think that now you have at least the elements to start looking into it and understanding it. Okay? So now we want to graduate, no? Want to graduate to the non-invertible case, to the case where we have more interesting fusion channels. And I think we will do it after the break, yes? And hopefully you will all come back. Okay, let's take a break of 15 minutes. Mm-hmm. Sì, 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 sì. This is on. Okay. So, I had a couple of interesting questions during the break, which reminded me that there is something more to say. So one question was about the relationship between the higher form symmetries and RG flows. No, there is one remark that is kind of obvious, but it's deep. No, which is that higher p form symmetries cannot be broken by relevant deformations. No, because the defect, the topological defect, have higher codimension. No, and so if you deform your theory with a point-like operator, no, it will always commute with the higher p-form symmetry. No, it will always commute. So if you have a higher p-form symmetry that emerges at some scale, no, it will always stay there. No, what can happen is that sometimes they can decouple. So that along the flow, all things that are charged with respect to them, they form a closed system, say. They are absorbed in some topological degree of freedom that don't interact anymore with your with your interacting part of the CFT, no? But they will always be there, okay? They never disappear. They don't break by deformations like this. So in particular, when you have higher groups, if you have a higher group, this establishes also some hierarchy. So the scale at which a one-form symmetry emerges is always going to be, I don't remember, greater or smaller, greater than or equal than the scale at which the zero-form symmetry emerges. No? And you can see it because when you try to fuse, what this diagram says is that if you try to fuse three higher form symmetry defects, you see that three zero form symmetry defects, you see that, so the interfaces are codimension 1, this point is codimension 2, no? And in codimension 2, we can always insert a one-form symmetry, no? One-form symmetries are codimension 2, no? So, if they form a higher group, when you try to fuse together the topological defects that are part of the zero-form symmetry, you must insert a one-form symmetry there, no? And so you cannot generate the zero-form symmetry before you have the one-form symmetry to begin with. Because the moment you try to fuse them, you generate it, no? And so the one-form symmetry should emerge before the zero-form symmetry, okay? So this is another constraint on RG flow, okay? So now let's discuss the non-invertible cases. In order to do that, we will use a bit more heavily these higher gauging operations. And so I wanted also to expand a little bit on that, no? Higher gaugings and condensates. So we spoke about them in the abstract yesterday, no? But let's consider an example. Let's consider a U1 one-form symmetry in 4 dimensions. So we know that the defects in this case are codimension 2 surfaces, which we have defined. No, they are this d theta 1 of sigma 2 exponential of I theta integral over sigma 2 of star J2. No? This would be the one-form symmetry defects. No? And so what is a U1, a ZK1 subgroup? No? Well, they are just those defects, no? Say of theta equal to 2 pi over k, no? So no, because they multiply like a group. This is a U1 subgroup. So if you multiply k of these spaces, they satisfy a relation like this, no? No. So out of these, we can get condensates of 2 kinds. No? You see, these are things that fill a surface. No? We are in 4 dimensions. No? The possibility that we have is we can use them to decorate a 3-dimensional submanifold of our space-time, or a 2-dimensional submanifold of our space-time. No? So in this case, we say, let's call it C of sigma 3, k, and in this case, we call it C of sigma 2, no? This would be the condensates, no? What does it mean? I told you, no? performing this Higher gauging is the same as decorating the surface with a consistent collections of these defects, no? But how do we do it in practice, no? So let's consider this one. This one, you see, this one will give rise to a condensate one-form symmetry, and this one would be a condensate zero-form symmetry, okay? Because they will still work, the gradient is still associated to the codimension of these defects in general, no? So the one-form symmetry, what is it? It's just all possible ways of filling this surface with insertions of these guys, and we can parameterize it as follows. We can use Poincare duality, use elements in the H0 of your surface with coefficients in the group you want to gauge. In this case, it is zk, no? And we just decorate the surface with their insertion. So we have 2 pi I over k of what? Of phi. It's a cohomology class, so the wedge is replaced by the cap product. And here we have the cohomology class associated to the higher form current for this U1 subgroup, no? And this is integrated over sigma 2, no? So it is very explicit, no? For this one, similar story, but now you see here I'm using H0 because the defect is codimension 2, so it is supported on a surface. It fills the whole of sigma 2, and so I have to use a class in H0, no? In sigma 3, no, the class that I have to use changes. I have to use a class in H1, no? Because the surface is codimension 1 inside of sigma 3. So I sum over H1 of sigma 3, again with coefficient in zk, and I do the same operation. Exponential 2 pi I k integral of alpha cap product with star of J2, no? So you see, the expressions for the condensates are extremely explicit. Once you know what are the topological defects, you can literally write them down. They are not mysterious. No, in general, when I drew it in the general discussion of yesterday, I had in mind some abstract topological defect, and so I was drawing these consistent networks. No, but if you have an explicit expression for the current, you can just write it down. Okay. So these are examples of condensates, no? And you see, this operation is the operation of gauging this symmetry on this surface, no? These alphas, they would be the analogs of the backgrounds for this zk subgroup, no? So, why am I being so pedantic about this? Well, because, so I told you about the condensates, they are associated to compact manifolds, but you can perform the same type of Higher gaugings also on manifolds with boundaries. And this is a very simple way of finding a non-invertible symmetry defect, finding defects that have some fusion rule that is non-invertible, no? The simplest way, probably. No? The so-called half space gauging. So these are like Higher gauging operations on manifolds that have a non-trivial boundary. No? So for instance, think about the case of the Ising model, no? That we discussed in 2 dimensions. No? You can consider building one of these half space gauging with respect to the Z2 symmetry. No? You can gauge the Z2 zero form symmetry, this eta line. No? And that one corresponds to inserting a consistent mesh of this eta line, no? and it will give rise to an interface between the Ising and the Ising modulo Z2. No? Now, we have to remember that this Ising modulo Z2 is also dual to Ising. No? And the composition of this half space gauging with the duality map between Ising and Ising Z2, so this one is the duality map. The composition of these two give rise to a topological line between Ising and Ising, and this topological line is the thing that we have called N, is the N line. No? So, sorry, I don't want to cancel that, I want to cancel this. No? So we see that N, no, this non-trivial defect line, arised in the Ising model by a condensate on half space-time of the Z2 eta line, no, composed with an interface that implemented this duality between Ising and Ising. No? And indeed, you can see that if you have this picture for N, no? So you see, gauging this gives rise to an interface between two different theories, Ising and Ising mod Z2. And then we have to identify them by the duality map. No? So from this picture, it's relatively straightforward to see that you have this fusion rule, no? That N times N is equal to 1 plus eta. No? How do we see it? So look at that picture. No? You have you want to write N times N, so you have Ising here. You put one of these half space gauging of the eta symmetry, and then you have your consistent decoration with a mesh of eta defects, no? And then you have the duality with Ising, which I call it I sigma, no? And now we have to insert N again, but we have to insert it with opposite orientation. Of course, N and N opposite orientation are equivalent defects in the case of Ising, but in this context it's important to do it in this way. And then here we have again our C a half eta, no? And we go back to Ising, no? And you see now we can compose them, no? When we compose this duality with itself, no? We just get the C half eta, C half eta, and we get this mesh in the middle, no? Here we have Ising, here we have Ising again, and here we have Ising mod Z2. And now, since these are all topological lines, so we can move them, there are topological interfaces, we can move these two together. As long as we move these two together, no, we are taking this mesh of lines that we have inserted, this condensation, no, we are shrinking it in such a way that it gets confined along a line, no? And once it is confined along a line, since each of these lines was one of these algebra objects that we have discussed, no, eventually you end up with a line which is 1 plus eta. No? So we recovered this fusion rule from the perspective of topological interfaces and gauging on half spacetimes. No? So this idea, no, this description of the duality defect in the Ising model extends in higher dimensions. No? So remember yesterday we had a comment about the fact that if we gauge a ZP form symmetry in d dimensions, we obtain back a ZD minus, Zn, sorry, a Zn d minus p minus 2 symmetry, no, upon gauging. No? So you see, if I consider a one form symmetry in 4 dimensions, This relation says that when I gauge at Zn one-form symmetry, I end back with a theory that still has a Zn one-form symmetry. No? So this is one ingredient. In the context of Ising, it was a zero-form symmetry in 2 dimensions, that when you gauge it gives back a zero-form symmetry. No? In 4 dimensions, we have to consider gauging a one-form symmetry. So it is precisely one of these condensation operations. No? And the idea is that we want to find a theory that has the property, so by this half space gauging, no, by this condensate, now we have to do it we have to have a theory that has a one-form symmetry, let's call it G1, no, which we can condensate, no, on a half space-time. And by this operation, we obtain an interface here between T and another theory, which is T modulo G1. No? So this is one thing that we can always do. But this one, you see, it's a topological interface between 2 different theories, T and T modulo G1. No? If the theory T modulo G1 also happen to have an isomorphism like I sigma with T, like a duality, then composing the half space gauging with the duality, we obtain an object, no, which we will call N, that has the chance of generalizing the N line in the Ising model, but now in 4 dimensions. Is it clear? So when you have a Higher P-form symmetry, you can form condensates by this Higher gauging operation. No? They give rise to a new collection of topological defects. Okay? You can do it on compact manifold, and then you just get topological defects of your own theory. But you can also do it on manifolds with boundaries. Okay? If you choose a manifold with boundary that has the appropriate codimension, so in this case it would be a sigma 3, no? Sigma 3 would be the boundary, no? So sigma 3 would be the boundary of a 4 manifold, no? Where we are performing this half space gauging, no? You can construct an interface between your theory and another one, no? So if you can gauge this symmetry, you can gauge it in the full space-time, and then you get a new theory, which is that theory gauged by this symmetry. But you can also gauge it on half of space-time, and then you get a topological interface. Along this topological interface, you are performing the gauging. And you go from the theory with ungauged discrete symmetry to the one where it has been gauged. It's important in this context that G is a finite group, so that performing the gauging is a topological manipulation of your theory. Okay? Yes? Yes. And the other half I'm not, exactly. And since I'm gauging a finite symmetry, this is a topological operation, and I can move this boundary at no energy cost, because gauging a finite group doesn't add anything to the action.
So what is the purpose of the action of symmetry?
Because, you see, this theory and this theory, they are different in general, no? I need another interface which says that this theory is dual to the theory I started from. No? So I need to obtain the non-invertible topological defect, say in the Ising model, we need a 2 statement. The first statement is that we can gauge eta. The second statement is that Ising modulo Z2 is dual to Ising. No? And indeed, N is the expression, is the manifestation of this duality of Ising. No? But it's the composition of 2 different, if you try to reason about it, exploiting the language of gauging in half space-time, is the composition of 2 statements. You can gauge that symmetry, and there is a duality interface. No? Composing the 2, you obtain a topological interface that goes from T back to itself. And therefore, it is an element, if you like, of the endomorphisms of the identity of T. No? like here, these half-spacing interfaces, they will become morphism from T to T modulo G. The duality would be another morphism from T modulo G to T, and composing them, if you are lucky, you get a map from T to T. This map will be our non-invertible duality defect. So, to give you an example of this logic, and that will probably help clarifying, let's go back to Maxwell theory, okay? So we have looked at Maxwell theory, and Maxwell theory is indeed a model that has a nice one-form symmetry, no? So we can try. Maybe Maxwell theory we can use it to build an example of this kind of behavior. And so in Maxwell theory, also has electromagnetic duality. No? So what is electromagnetic duality? Electromagnetic duality is a quantum property of Maxwell theory. So you have to consider the path integral. No? The path integral of Maxwell theory has the following form. No? 1 over 2 e squared, integral of f2, wedge star f2. No? In this path integral, we are saying that f2 is the curvature of a gauge connection. No? But we can rewrite this path integral as follows. Introducing a Lagrange multiplier field, and instead of integrating over A1, integrating over F2, but now considering it as a form, without requiring that it is the curvature of a connection, and imposing that it is a curvature of a connection via the Lagrange multiplier. You see now, the fact that the Bianchi identity is satisfied is no longer a consequence of the fact that we are requiring that f is d of A1 locally. It is a consequence of the equation of motion of this field, of A1 dual. Okay? You just vary the action with respect to A1 dual, and you get that df is 0. So eventually, these two path integrals are the same, give rise to the same theory, but it's just a convenient rewriting of it. No? Now, you see that in this new path integral, F2, the Maxwell field, no, enters quadratically. So we can integrate it out. No? Integrate out Maxwell, integrate F2. What we obtain, well, we have to say we have to use the equation of motion, no? So if you look at the equation of motion for F2, you can see that it is solved by setting 2 pi over e squared star F2 to be equal to d AD1. No? Just by varying the action with respect to the field F2. No? So we can decide that this is a good definition for a dual field, F dual. No? And with this definition, we can plug it back into the action we started from, integrating out F2, we end up with an integral over A1 dual of an expression which looks exactly like the original Maxwell equation, no? But with a different coupling. The new coupling is related to the original coupling by this famous relation. With the ingredients on the board, you can derive it. Okay? So we have established the equivalence of Maxwell theory with coupling E squared, with Maxwell theory with another coupling upon a duality transformation. Okay? Yes? Yes? No, I'm not imposing this. No? here it comes as an equation of motion, no? Ugh. Sorry. Uh-huh. You obtain you have to ask that the periods of A1 dual are quantized, no? You have to it's a U1 field. So because of that, eventually you end up with a connection. F dual becomes a connection. Okay. So this give rise to an interface of the type I sigma, if you like, no? Between Maxwell theory with a given coupling and Maxwell theory with another one. No? So we have, schematically in this type of language, we have that Maxwell theory with coupling is E over 2 pi, no? Has an interface, topological interface, which we can call I sigma, with Maxwell theory with coupling 2 pi over E dual, no? So no, sorry. Let's say like this. Maxwell theory with coupling E is equivalent to Maxwell theory with coupling 2 pi over E. No? Just by plugging in. No? So this interface is given by EM electromagnetic duality. No? And it is one topological interface. We can also build another topological interface in Maxwell theory because we know that it has this one-form symmetry and this magnetic, both the electric and the magnetic one-form symmetries. No? So what can I erase? Let me erase this board. So Maxwell theory has U1 electric and U1 magnetic. In particular, we can choose a Zn1 subgroup of this guy. No? As we did before, no? We choose a subgroup of the one-form symmetry and we form a condensate. We can do the same operation now for Maxwell theory, choosing a subgroup here. No? And gauging it exactly with the same manipulation that we have mentioned before is something that we can absorb in just a change of the quantization condition. So it's equivalent to take the electric Maxwell field to 1 over n times A1 and the dual Maxwell field to n times A dual. No? So this gives rise to a different interface between Maxwell with coupling E, and then here we have the half space condensate of the Zn one-form symmetry. No? And here we obtain Maxwell, but now with coupling 2 pi over n times E. No? Just by half space gauging of this subgroup of the electric one-form symmetry. No? So these are two different topological interfaces between different copies of Maxwell. No? So we are in a situation where we go from a theory to a different theory by a topological interface. They are different. No, the coupling is different, so they are different theories. No? However, we can ask, can we compose them? No? We want to get to a diagram like this. No? So can we compose them? What happens if we compose them? We take Maxwell with coupling E, we take I sigma, and we take this C to the half Zn 1. No? No, I did it in the opposite order, of course. Sorry. So this first one, no, will map to Maxwell with coupling. Sorry, I did a mistake. This one is just n times E. Apologies, I was going a bit too fast. So here we go to coupling n times e, and by the EM duality we invert this over 2 pi, no? Okay? So just shifting the fields according to this equation give rise to this shift in the coupling, no? And composing the Maxwell with the coupling shifted with the EM duality, we obtain a relation where we have Maxwell at this value of the coupling, no? And so the question is there a value of E such that when we compose them, it stays fixed with respect to this operation? No? And there is. If you choose an E, which is the square root of 2 pi over n, as your coupling for Maxwell theory, E star here becomes E star there. And so you see that if you choose a coupling for Maxwell that has this value, you obtain a composition of a half space gauging interface with a duality interface that fits this paradigm. Okay?
We can also choose I sigma to just be C1 hat to just go back to the example.
Oh yes, but in that case it wouldn't be non-invertible. No? I want a non-trivial operation. No? The name of the game in this last part of the lecture was can we find something that has a fusion rule which is more interesting than group-like? And we reinterpreted what we did in the Ising model in terms of half space gauging interfaces and duality interfaces. And we see that with that language, we can construct, using the tools that we have developed in these lectures, a non-invertible defect in Maxwell theory. Maxwell theory. No? And credit for this work go to some very nice papers, which I should mention. One is by Kaidi, Omori, and Zheng. Uh, 2021. And the other is Choi, Cordova, Lam, Xin, and Shao, hopefully, same time. Okay? So what are the features of this duality defect? So you see, by the same token, no, if we consider the fusion of so we call our non-invertible defect, we call it C half Zn1 composed with I sigma, no? And by the same reasoning as before in the context of the Ising model, if we take n and we fuse it with n bar now, no, what is going to happen? No, same picture. We have our C half, we have our I sigma, we have our I sigma, we have our C half. No? Here we are gauging the Zn1 form symmetry. Here we are gauging the Zn1 form symmetry. This is a duality. When we compose it, it simplifies. It just gives rise to 1. No? So you see what happens. No? This is supported on a sigma 3. This is a sigma 4. Is the full of space-time. These are inserted. No? This is inserted on sigma 3. This is inserted on sigma 3. No? They fuse. This becomes a whole region where we have gauged this Zn1 form symmetry. When we bring these two together, what happens to this region is the same that happened for the line of the Ising model. It was confined on a line in that case. In that case, it is confined on this sigma 3, this surface that separates these regions, no? This interface. And so we find that if we take n of sigma 3 and we fuse it with n of sigma 3, the result is a condensation defect for Zn1 on the same dimensionality. Okay? And remember, we know what is the expression of this guy. This guy is something that looks like the sum over h in h1 of sigma 3 in Zn of the exponential, no, of some insertions, no, of the one-form symmetry, no, on the Poincaré duals of these alphas. Okay. So if you look at this, this is the higher dimensional version of our good old friend 1 plus eta. No? It's just that now the symmetry defect that implements the Zn symmetry is not just a Z2 line, but it is a one-form symmetry insertion. And what we are decorating it with, we have to sum over all the two cycles inside of this three manifold. No? So this is an example of a non-invertible defect in 4 dimensions. No? The reason why it is non-invertible is indeed that when it fuses, it gives rise to this infinite sum. Okay? Which is, however, just a condensation interface. No? So, yes.
Why is it obvious that the interface between Maxwell and Boole is upright?
Because we proved it. It's just a change of variable in the path integral. You see, it's a change of variable in the path integral, no? And so you can use one path integral on one half of the space-time, the other in the other, and since they are related just by a change of variable, there is no dependence on the position where we decide to do the change of variables, no? It is topological, but it is an interface between two different theories. The Maxwell, the electromagnetic duality, no, in general, is stating that you start from a theory with coupling E and you go to a theory with coupling 2 pi over E, no? But this is a duality, so it is something that it's an equivalence. And of course, it will act also, no? So the electrically charged particles will become the magnetically charged ones, no? And this is how it will act, if you like, on the point-like operators, no? Okay? So, these operators is a very good question. No? So we have we spoke about it. We say if we have a topological defect, we have to see whether it acts or not on some extended operators in the theory. No? And the non-invertible duality symmetry, no, will, since it is built out of gauging the one-form symmetry, it will have an effect on the line operators in your theory that have a charge with respect to the one-form symmetry that we are gauging along the interface. So if you take one of those, like you have a line operator inserted along a line, no? If it is charged with respect to the one-form symmetry that we are gauging, no? This is our defect. We can take this defect and move it past this line. And once we have done that, this line becomes a different line, which is no longer genuine because it was charged and we are moving it through a region where this symmetry was gauged. So it becomes non-genuine. No? And it picks up an attachment of this Zn one-form symmetry. No? So you see, you remember when we spoke about the action of the duality defect in Ising, it takes sigma and it mapped to mu. No? We had an operator and we have mapped it into a twisted sector operator from an order to a disorder transition. The same thing happens for the higher duality defects, but now it takes a line operator and it maps it in a twisted line operator. This is not a genuine line because it comes with a topological attachment of one of these higher form symmetry charges, which is related to the charge that your line had with respect to the one form symmetry that you were gauging to begin with. No? So there is a generalization of the order-disorder transition, but now on the spectrum of extended operators. If you have if you start from Maxwell theory, yes, no. But this discussion is general. You can, whenever you have a theory that has a one-form symmetry that you can gauge and a duality, this will apply. No? And so there is this order-disorder transition. There is but the spectrum, again, is not about the spectrum of point operators now. It is about the spectrum of extended operators. And again, we will have twisted spaces. No, we have the spectrum of the genuine operators, and then we have the spectrum of, then we have the twisted sectors. But now the twisted sector will involve all extended operators that we can insert in our space-time. No? So the story from 2D generalizes in higher dimension in a very more and very rich way. No? Moreover, there is also a notion of a quantum dimension for these gadgets, which you can compute again from the definition. And it turns out, if you normalize things properly, which I think I haven't, this is the result. No, it's related to the fact that you can always normalize the condensation defects with the volume of the gauge group. No, so there is a non-trivial quantum dimensions, non-trivial. But while for the topological lines, the quantum dimension was the value of the line on the circle, in this case, the quantum dimension is the value of the defect on the sphere. No? So we have seen how to construct them. Now there are two more things that I wanted to discuss today. One thing is about constraints on the dynamics. You remember in 2D we have seen that just having a non-invertible defect led to something that we could say about the infrared, that the infrared was not trivially gapped. So this is one thing that I wanted to discuss. And then we also saw how to build word identities from these extended, from the topological lines. And so we can do the same thing with these non-invertible defects in 4 dimensions. And this is another nice example that I want to discuss. Question, do you want to have a break before we do that, or we go straight? Or maybe we discuss we can discuss the constraint on the infrared, and then have a break, and then do that. How do you feel? Like last option, all in favor? Okay. So let's discuss a dynamics constraint, and then after the break we will discuss the word identity. So what I want to illustrate is that if we have an RG flow that preserves this type of duality defects, it constrains the structure of the possible gapped phases that can realize it. No? So I want to consider an RG flow preserving preserving n, no? We can call it n0. No? Preserving n0. And And we want to ask ourselves what happens in the infrared. So can the IR phase be trivially gapped? So what does it mean to be trivially gapped in 4 dimensions? It means that it is described by a 4-dimensional SPT, they are called. It's called, it's an acronym for symmetry protected topological phase. It is a very fancy way to denote a phase. Okay, just a phase. Kinda, no? So yes. Trivially gapped means that there is no degeneracy in the ground state. No? So there is only one state in the infrared, and the freedom that we have is to assign to it a given phase. No? So we consider the case of Zn1, where n is odd, for simplicity. But one can do also the case where n is even, but the argument is essentially the same. So when n is odd, the possible SPTs that we can obtain that has this one-form symmetry have the following form. So remember, I told you, if you have a one-form symmetry, you cannot break it along a flow. No? So if you get this infrared which is trivially gapped, you have to obtain a theory that still has a Zn one-form symmetry somehow. No? And for this reason, we have this type of action. It will depend on a background for this one-form symmetry. No? So if the greater common divisor here, n and p is equal to 1, we can write this expression in terms of Zn gauge fields. So we need to require it. No? And this is an SPT. No? Otherwise, if the greater common divisor of n and p is a different number, then you get a theory that is not just a trivial phase once you quantize it. There are some becomes more complicated once you gauge this A2. No? So now, in order to construct the duality defect, we have to insert these gauging interfaces. No? So inserting a topological interface is a topological manipulation of the theory. So it is something that survives along the RG flow. No? So we should be able to insert a gauging interface also for this SPT. We can insert so what happens if you gauge it? In general, you take an SPT that depends on this one-form symmetry background. When you gauge it, you just sum over all possible ways of decorating. Now we are doing it in 4 dimensions, the 4-dimensional manifold with respect to the same group. No? You take the action of the SPT, you evaluate on the field that you want, no? And you get something like this. Something that is analog to the expression that we had for the condensates. No? So this on the right hand side, we have taken our SPT and we have gauged the one form symmetry. Now the theory has a chance to have our duality defect if it satisfies this equation. No? Because we want it to be invariant with respect to that composition, and at the level of the SPT, this translates into this equation here.
So here you have already gauged
Yeah, so the idea is that if our RG flow is preserving the duality defect, then, and the infrared is trivially gapped, so it is described by an SPT of this type, and n is odd, then the SPT will be compatible with this non-invertible defect only if it satisfies this equation. No? So this is an equation on the ZSPT of A2, which I defined over there. Okay? So when we perform the gauging, what do we obtain here? We obtain a sum over A2 of the exponential of 2 pi I p over n, integral over x, A2 cap product with A2, plus 2 pi I over n, integral over x. X is our space-time, no? Of A2, no? And so you see that again, A2 enters quadratically in this equation, so we can integrate it out, no? And we can integrate it out like this. Imposing this equation modulo n, because these are Zn valued fields, no? Notice that we can divide by 2p because we have assumed that n is odd. Otherwise, this part of the analysis would be a bit more complicated. Plug it back into the action, and you see that you get that this is equal to the sum. No, it becomes equal to, we are integrating out A2, so we remove the sum over that field, and we plug in the expression for the equation of motion, no? And we get an expression which is like this, e to the minus 2 pi I over 4 np. Integral x A2 cap A2. So you see, our original SPT had that expression. Upon performing the half space, upon performing a gauging of the Zn1 form symmetry, we obtain this expression here. It is possible to have a duality interface only if this coefficient matches that coefficient modulo n. So we want that p over n is equal to minus 1 over 4np modulo n, which can happen only if p squared is equal to minus 1 modulo n. Okay? So you have a condition. It doesn't happen always. X is space-time, yes. It's a 4-dimensional manifold. The place where we are integrating our field theory, no? Where our field theory lives. So if your theory is trivially gapped, then in the infrared it will have a partition function that looks like that SPT. No, so it is indeed just a phase. And however, that phase has a one-form symmetry which we can integrate over. And the invariance with respect to that, so the fact that we can define this half space gauging and that it preserves the theory is related to this condition. No? So in the case of the SPT, this condition here is the equivalence of the fact that there is the duality between the gauged theory and the non-ungauged theory. No? P is no, P is a prime number, and it satisfies this equation modulo n. No, it's modulo n. Yes, yes, no worries. Yes. And so, like, this is solvable. This equation is solvable provided minus 1 is a quadratic residue in Zn, no, which is a statement that you can that there is a if you work modulo n, no, minus 1 is a quadratic residue. No, we're just saying in word what is written here. And you can show that this happens if you take a factorization of n into prime numbers like this. When all the PIs are equal to 1 modulo 4. Have to believe me on the number theory. No? So it is a non-trivial condition. No? It's not obvious that this is satisfied. So if this condition on n is met, no, then the whole story is consistent. But if it is not met, then the theory cannot be in a trivially gapped phase. Okay, so if this condition on n is not met, the theory cannot be in a trivially gapped phase. So you see that so this is a direct analog of what we have remarked in the context of 2 dimensions. If in 2 dimensions you had a topological line that had a quantum dimension that was not an integer, a positive integer, then we showed that it couldn't end up in a trivial vacuum, a trivial theory. Here we are in 4 dimensions, so the notion of a trivial theory is a bit more fancy, no? But we can constrain it requiring that it has a Zn, that it is a Zn1 SPT, because we know that Zn1 was there to begin with, and exploiting the classification of those, when n is odd, we know that it has this form. And we see that having an RG flow that preserves the duality defect and ends up being in a trivial SPT can happen only provided n satisfies this condition. So there are cases where this is not not solvable, and in those cases the infrared of your field theory, if it has this duality defect, has to be non-trivial. No, it either has a multiplicity of ground states, in which case you have an effect like symmetry breaking, or it has to be gapless, so it has to be a CFT. Okay. So this is an example of a constrained energy flow that arises from non-invertible symmetry. Yes. We don't, like I just said, we did n odd because the number theory in this case is easier. In n even requires more fancy stuff that I didn't want to introduce. You can also do it. There is a similar constraint when n is even, and yeah, there is. If n is odd, this is it, and if n is even, there is a similar criterion different than this that you have to check. Yes. Okay. Hmm. We used it when we have required that there is a duality interface between the gauged theory and the ungauged one. No? The condition, the number theoretic condition on P and N comes by requiring that the SPT that you start from is mapped back to itself upon gauging the ZN1 form symmetry, which is the SPT version of the statement that there is a duality interface between the gauged theory and the original one. No? Is the fact that this is a two-form background. No? Is a two-form valued in Zn. The one form symmetry, like this is an SPT for this Zn one form symmetry, which is the statement that it is a phase that depends on a choice of a background, which is this A2 Zn valued gauge field. Yes. Yes, because we have to match the whole structure. Okay. So we have a break, and then we speak about the word identity.